Paradoxes have to do with valid arguments, and it is the concept of a valid argument that we are going to explain in this first video. Now, that an argument is valid, generally speaking, means that it is impossible for its premises to be true and its conclusion false, right? So consider the following argument. If Socrates is a man, then Socrates is mortal. Socrates is a man, therefore Socrates is mortal. Now, this argument is clearly valid, right? But that the argument is valid does not mean that its premises are true or that its conclusion is not false, right? And not even that, as a matter of fact, it is not the case that the premises are true and the conclusion false. That the argument is valid means that it is impossible for its premises to be true and its conclusion false, right? So consider this second argument, right? If Socrates is a Martian, he will invade Earth. Socrates is a Martian, therefore he will invade Earth, right? Now, this argument is clearly valid, right? But the conclusion, at least I don't believe that Socrates is going to invade Earth, so I better not believe some of the premises, right? Because if I believe the premises, I am bound to believe the conclusion, right? This is validity. Validity is a matter of, it is impossible for the premises to be true and the conclusion false, right? If it were true, if the premises were true, the conclusion will have to be true as well, right? So far, so good, right? This is very nice. But the problem is explaining what impossibility is in the present context, right? Because the history of philosophy is crowded with literature on what modal notions mean, right? Fortunately, we've got a rather simple analysis of the notion of impossibility involved in valid arguments, right? We say, and this is like our official general definition, we will say that an argument is valid when there is no interpretation of the non-logical vocabulary where the premises are true and the conclusion false, right? This means that in a valid argument, we should distinguish between logical and non-logical vocabulary. So for example, here, Socrates is a man. This will be non-logical vocabulary, right? And Socrates is mortal. This will be another proposition, simple proposition, non-logical vocabulary. And the conditional is part of the logical vocabulary, right? So I repeat, and this is the definition that we will use in this course, that an argument is valid means that there is no interpretation of the non-logical vocabulary where the premises are true and the conclusion false. Right, I'll see you in a minute. In the previous video, we explained what logical consequence is, what does it mean that an argument is valid. And we said that an argument is valid just in case there is no interpretation of the non-logical vocabulary where the premises are true and the conclusion false, right? Now, I want you to notice that this definition of logical consequence, in order to specify a particular notion of logical consequence, we have to specify a language in which we give a neat separation of logical and non-logical vocabulary, and what an interpretation for that language is, right? And this is what we are going to do right now for the classical propositional language, right? So the classical propositional language, right, contains a vocabulary divided in non-logical and logical vocabulary. The non-logical vocabulary is composed of propositional variables, right? So the propositional variables are like the bricks, the most basic sentences of our language. And the logical vocabulary is composed out of conjunction, disjunction, negation, conditional, and a couple of parentheses, right? So these logical connectives are like the glue to put the bricks together, right? And so that we can specify a set of rules that will tell us which sequence of expressions of the vocabulary are part of the language, right? This is pretty easy. Probably all of you know that, so I'm not going to comment on that. You will see them on the notes. So that's language, right? Now let's go for the semantics. Now, an interpretation intuitively speaking, an interpretation is substituting the variables by sentences, right? Because these variables are just telling you, here you should plug in a sentence, right? Now that's the intuitive idea of an interpretation. But it turns out that in logic, we don't care very much about what sentences say, right? So we make a big jump of abstraction, right? This is a big idealization. All what matters for us is whether a sentence is true or false, right? So we will take that an interpretation is a function assigning truth values to the propositional variables, right? An interpretation is an assignment of truth values, true, 1, false, 0, to each propositional variable. This is a huge idealization, right? But this is the way logic works. Now, after we have considered what is an interpretation for the non-logical part of the vocabulary, we would like to know how an interpretation extends to all the formulas, right? So you give an interpretation for the most basic formulas, and then we would like to know how this interpretation for the basic formulas extends to all the formulas of the language, right? And this can be easily done by some clauses. This is called a recursive definition. We won't fuse too much about what a recursive definition is, but intuitively speaking, we are set the conditions of a complex formula. So when a complex formula is true in terms of the components, right? So that you start to analyze a complex formula and you can go down to the propositional variables, right? For the case of conjunction, we will say that a formula of the form A conjunction B takes value 1 is true, just in case both A and B take value 1 in that interpretation, right? For the case of negation, a formula of the form negation A is true in an interpretation just in case the unnegated formula is false in that interpretation, right? So this should match our intuitions about conjunction and negation, right? So let's see how this works with a particular example, right? So given an interpretation for the propositional variables, this interpretation will induce a unique truth value for any formula of the language, right? So consider the following example. We've got here this formula, right? And we've got an interpretation for the propositional variables in that formula. This interpretation gives us the value 1 for P, the value 0 for Q, the value 1 for S, and the value 0 for R, right? So we can analyze this formula in a tree, and you can see that for this particular case, right, since P takes value 1 in this interpretation, and Q takes value 0, right, by the clauses of conjunction, right? Conjunction takes value 1 just in case both take value 1. We've got here that P takes value 1, but Q takes value 0, right? So this is going to take value 0. P conjunction Q is going to take value 0. Now we've got this formula here, right? So P conjunction Q takes value 0, but the disjunction, in order to be true, requires just one of the members to be true, and S takes value 1, right? So that's enough to make true this disjunction. So this is going to take value 1 in that interpretation. Now R takes value 0 in the interpretation, and this, the antecedent of this conditional, takes value 1, right? And this is the unique case in which the conditional takes value 0, right? So this is going to take value 0, and that was what it is sometimes called the main logical sign of a sentence, which tells us the truth value of that sentence. And in this interpretation, this sentence takes value 0, right? We've got all the ingredients now to give our definition of logical consequence, which we will make soon in the next video. Okay, so we've got everything we need to define precisely what logical consequence is for the propositional language, right? So we say that logical consequence So there is logical consequence when there is no interpretation where the premises are true and the conclusion false. We have defined precisely the propositional language, right? And we have defined precisely what an interpretation is, right? So we've got all the ingredients, right? We can say that a conclusion A is a logical consequence of a set of premises gamma. Just in case, so here gamma is supposed to be a set of sentences, right? So A is a logical consequence of gamma, just in case there's no interpretation where all the premises take value 1 and A takes value 0, right? So there is no interpretation where all the premises, all the gammas take value 1 and A takes value 0, right? So this meshes with our previous ideas, right? Now we are going to give a slightly generalization of this notion of logical consequence. So very often logical consequence is defined just for multiple premises to single conclusions, but we are going to consider the case where we've got multiple conclusions, right? So we can have a set here on the right of the logical consequence symbol, right? Why do the so there are like philosophical reasons to justify this use. We are going to do it just for very, very pragmatic reasons, right? That it allows us to express some facts, particularly related to the concept of duality that we will explain later. Okay, so we will say that a set delta is a logical consequence of a set gamma, just in case there is no interpretation where all the gammas take value 1 and all the deltas take value 0, right? I repeat it. Delta is a logical consequence of gamma just in case there is no interpretation where all the gammas take value 1 and all the deltas value 0, right? Or in other words, in any interpretation where all the gammas take value 1, at least one delta takes value 1, right? So that's the idea. Now some examples. So come with me. So for example, the particular case, right? Our first definition for single conclusions is a particular case where the delta, the set delta in the conclusions contains just one element, right? So that A is a consequence of gamma means that the set containing A is a logical consequence of gamma, right? Now we can talk about valid sets, right? We can say that a set is valid when this set is a logical consequence of the empty set, right? And in order to see what this means, you have to look just at the right-hand side of the definition. So come back to the definition of logical consequence. So suppose that this is empty now, right? So delta is a valid set just in case there is no interpretation where all the deltas take value 0, right? So delta is a valid set when at least in every interpretation, at least one delta takes value 1, right? Examples of valid sets. Well, we've got that this is a classical validity, right? P disjunction negation P, right? This takes value 1 in every interpretation, right? So this is a classical validity. But this is a classic set, a valid set, right? Because P, the set containing P and not P, right? In any interpretation, at least one of them will take value 1, right? So this is an example of a valid set, right? And the same goes for the premises. So we can say that a set gamma is unsatisfiable, right? A set gamma entails the empty set when, and this is the dual notion, so suppose now that we've got only premises, no conclusions, this is valid just in case there is no interpretation where all the gammas take value 1, right? So you forget about this part of the definition now, right? So a set gamma is unsatisfiable just in case there is no interpretation where all the gammas take value 1, right? So for example, P conjunction not P is classically unsatisfiable, right? But also the set containing P and containing not P is classically unsatisfiable, right? Perhaps you can see that there are some symmetries here, right? We will talk about this later. So that's it. So far, we have actually defined classical propositional logical consequence, right? So we gave the language, we gave the semantics, and the definition of logical consequence. Now, at some point, it might not be obvious what a given statement of logical consequence holds, right? So we would like to have not just the definition of logical consequence, but some means to decide in a given, for a given statement of logical consequence whether it holds, right? And this is what we are going to present now. So we are going to present a proof theory called tableaus, right? So basically, the idea behind tableaus is that you've got a set of rules, right? You've got some sentences, gamma sub 1 to gamma sub n, right? And you've got some set of rules to chop that sentences and start constructing a tree, right? A tree is a mathematical structure, right? We don't fuse too much about the definition, but it's something that starts from an initial list, and at some point it might open a branch, or it might not open a branch, right? It's a particular ordering. So we've got a set of rules to chop the initial list of sentences, and the tree, once we have chopped all the sentences, the tree will tell us whether this initial list of sentences is or is not satisfiable, right? So as we shall see later, the rules, so the tree is like a systematic search for an interpretation satisfying this initial set of sentences, right? Now, you might wonder now, well, I don't care about satisfiability, I care about logical consequence. Okay, that's right, that's a good point. But the thing is that you can, in classical logic, you can always translate any question about logical consequence into a question about satisfiability. And this is the trick we are going to use, right? Just to remind you, delta is a consequence of gamma, just in case there is no interpretation where all the gammas take value 1 and all the deltas take value 0, right? Now, delta takes value 0 in an interpretation, and this is part of the meaning of negation, just in case, if and only if, the negation of delta takes value 1, right? And this is the definition of an unsatisfiable set, right? So delta is a logical consequence of gamma, just in case there is no interpretation where all the gammas take value 1 and all the deltas take value 0, but this is equivalent to there is no interpretation where all the gammas take value 1 and the negation of the deltas take value 1, right? Which is another way to say this. This set is unsatisfiable. Just to recap, right? Delta is a logical consequence of gamma, just in case the set containing all the gammas plus the negation of the deltas, right? This is the union symbol in set theory. The gammas plus the negation of the deltas is unsatisfiable, right? So suppose now that someone asks you, well, is delta a logical consequence of gamma? How can we use tableaus to answer this question? Well, that's easy. You've got just to write as your initial list all the gammas and the negation of the deltas, right? Right? And then apply the rules that we are going to explain in a minute. So we said in the previous video that the tableau method is a way to check whether a given set is satisfiable. Given this connection between logical consequence and satisfiability, all we need to check to know whether delta is a logical consequence of gamma is to check whether this set, the gamma plus the negation of the deltas, is or not satisfiable, right? Okay, so our tree will start with a list of formulas, right? We have to place the gammas in the first place, and then the negation of the deltas in the second place, right? And the three rules in order to extend the tree are like a systematic way to search for an interpretation making through all the formulas in this initial list, right? So the three rules can be read from the truth conditions of each logical connective, right? So for example, suppose that we've got a formula of the form A conjunction B in the tree, right? In order to analyze this formula, we have to extend the tree with two new formulas in the same branch, right, A and B. Why? Because there is just one case in which A conjunction B is true, namely the case where both A and B are true, right? That's why we don't have to consider just, we have to put both formulas in the same branch, right? Because there is just one case in which a formula of the form A conjunction B is true, right? Now, a different case is that of the negation of a conjunction, right? So a conjunction is false in three cases, right? When either one of the conjuncts is false, when the other is false, or when both are false, right? So there are three cases where the negation of a conjunction is true, right? The case where one of the conjuncts is false, and the case where the other conjunct is false, and the case where both are false, right? So our tree rule will have to cover all the possibilities, right? That's why when we've got the negation of a conjunction, our tree will open a branch, right? So we will consider in a separate way what happens when one of the conjuncts is false, and that's why we write negation of A, and we will consider what happens when the other one is false, right? In this way, we make sure that we search for all the possibilities, right? All the other three rules work in a similar way, right? So we will say that a branch of the tree is closed whenever it contains a formula and its negation, right? When a branch closes, the tree is telling us that this attempt to find an interpretation doesn't work, right? Now, a tree closes whenever all its branches are closed, right? If the tree closes, then this means that the initial set of formulas is not satisfiable, right? Now, it might happen that some branches close, some others don't, but you have applied all the rules to the formulas that appear in the tree, right? So there is nothing left to chop, right? Or nothing left to analyze. In that case, the tree is open, and it's telling us that there is an interpretation satisfying the initial set of formulas. So in order to make these things more clear, more precise, we're going to make an example right now. So we explained in general how the tableaus rule, but the nice way to see how they work is with an example, right? So we've got here a logical consequence statement. The premises say P conditional Q conjunction R conditional S, right? And the conclusion is P conditional S disjunction R conditional Q, right? And let's gonna check whether this statement of logical consequence works, right? So the first thing we have to do is to list the premises and negate the conclusion, right? So we've got already here the premises, and I'm gonna put as the second line of my tree is going to be the negation of this disjunction. Now, this is a small trick you should take care about. So here I wrote the disjunction without outermost parentheses, right? So be careful, right? If you want to negate the disjunction, you should include the parentheses. Otherwise, you will be negating just this part of the formula, right? So let me modify this. Okay, so we've got the premises and the negation of the conclusion, right? Now, let's gonna check which rule should we use to develop the tree, right? So we've got the premise is a conjunction, so we can use this rule here, and the negation of the conclusion is the negation of a disjunction, right? Which is this other tree. You can apply the rules in any way, in any order you like, right? Usually the easiest thing is to apply first the rules that do not open any branch, right? So let's do it here, for example, right? Conjunction, so extend the tree with a single branch in which you write both sides of the conjunction, right? So P conditional Q and R conditional S. That's the first thing. Second, so we are done. You can mark this and you can forget about that. Negation of the disjunction, right? So a disjunction is false, right? Just in case both members of the disjunction are false, right? So the negation of a disjunction is true just in case both disjuncts are false, right? So let's do it. Right. Okay. And we are done with this, right? Now, which rule should we apply to this formula, this or this other one? Well, let's apply the rule for the formulas that do not open branch, which are these ones, right? So a conditional is false just in case the antecedent is true and the consequent is false, right? So P and not S for this formula, and R and not Q, right, for this one. So let's apply now the rule for this one, for example. Okay, so let's apply the rule to this one, right? So P conditional Q, A conditional B, that's going to be true whenever either the antecedent is false or the consequent is true, right? So this is a case where the tree opens a branch, right? And we have to write the negation of the antecedent in one branch and the consequent in the other, right? So we've got here P conditional Q. This tree opens a branch here, and we write not P and Q, right? Now, it turns out that we've got in this branch here, right? This is one of the branches of the tree is this one. And in this branch, we've got Q, and we've got the negation of Q, right? So the tree is telling us this is a no option, right? So if you want to make all the formulas true, taking this route, this has no way out. You cannot do it, right? So you've got here a contradiction. So you can mark that the tree closes on that side, right? Now, on this other branch, we've got not P, but we've got P as well, right? So we've got another contradiction, a formula and its negation. So again, the tree is telling us, if you try to find an interpretation that way, you won't find it. There is no interpretation making true the formulas that way. And since our tableau method is general enough to consider all the possible interpretations, this tree in which all the branches are closed is telling us that this initial list of formulas, right, this is not satisfiable. That is, that this logically entails this without the negation, right? Okay, so that's our proof. This is the way trees work. We are done. So in this last video, in this last example, we're going to see what happens when there is no consequence relation, right? So when the statement of consequence does not hold. So the procedure is basically the same. So we list the premises. We've got just one premise here, and we negate the conclusion, right? Again, be careful. There are no outermost parentheses, so you should add them, right? Okay. So not S, conditional, not P, and you negate that, right? And now you start to apply the rules, as always. So we've got a conditional, and we've got the negation of a conditional, right? If you see the conditional opens a branch, the negation of a conditional does not open the branch, so we go for this one first. That's the easy option, right? So this is not S and not P, and we are done with this, right? And now we've got to go for this one, right? So this is the main logical sign, right? So we are going for this conditional, not for this one, right? So this rule opens a branch. We've got to negate the antecedent, right? Write the consequent. We've got that in this branch, right? In this branch, we've got S, and we've got the negation of S, right? So this branch closes, right? We don't have to inspect it further, right? Because this branch is always telling us, no way, right? There's no, you won't find an interpretation that way. We continue with this branch. Now we've got the negation of a conditional, right? And that's easy. Antecedent and negation of consequent, right? Okay. And now, what happens? Well, it happens that in this branch is open, right? There is no formula and its negation in this branch. We've got not Q, we've got P, we've got double negation of P, not negation of P, right? Double negation of P. And we've got negation of S, right? So this branch, you can mark it this way. I like to do it this way. You can mark it, that branch is open. Now, the nice thing of the tableau or the trees is that they are so kind that they are going to give us the hint, you know, to construct an interpretation satisfying the initial set of formulas, right? And the recipe is very easy. So you've got to clip the open branch, and for any propositional variable in the branch, right? Sorry, for any propositional variable whatsoever, if that propositional variable is in the branch, the interpretation assigns to that variable 1, right? True. If the negation is in the branch, it assigns the value 0, right? Now, since the branch is open, the interpretation is consistent. It won't find a formula and its negation. So the interpretation won't assign this to the same variable different truth values, right? Which is part of the trick, right? And if the variable is not at all in the branch, you can assign the truth value you like, right? So let's do it for this. We've got negation of Q, right? So our interpretation should assign to Q the value 0, of course. We've got P, right? So the interpretation should assign to P value 1. Not P, of course, will have value 1 as well. And we've got negation of S, so the interpretation will assign to S the value 0, right? Now, the funny thing is that this interpretation makes this true and makes this true. This means that this interpretation makes this true and makes this formula without the negation false, right? So this interpretation is what we can call a counter model, right? A counter example, an interpretation showing that there was no logical consequence. This is how trees works, logic works. I'll see you in the next unit.